Hello everyone, in this video we are just going to generate pulses of required frequency, period and duty cycle with the help of pulse width modulation in Renesas RL78 by F14 series microcontroller. Let's get started. So now let us try to open the CubeSuite Plus for CCRL IDE for creating our project for the microcontroller. You can see in this IDE opened. I'm just going to create my new project. Just click on the project tab in the top of the window and then hover over this create new project and click on it for creating your new project. And in the window that is popping out, just type in the microcontroller name. In my case, I'm just typing R5F10PPJ and you can see the highlighted microcontroller will be selected by default. So just cross verify that the pin number is correct for your microcontroller. In my case, it is 100 pin, it is correct. So I'm just leaving it. Or if it is anything different like this one or this one, just click on select anything as per your requirement. Just left click and select it as per your requirement. And once after selecting the microcontroller, just provide a name for your project in this project name tab. I'm just providing it to be Pro. And in place of this place tab, just click on this browse button for selecting the repository or directory in your local folders where you want the project to be stored. So let me just make a folder right over here, RL78. And I'm selecting that folder and I'm clicking on the create button for creating my project for this particular microcontroller selected. You can see on the left of the IDE we are having a particular tab called project tree. So this particular tab will be containing several segments of the microcontroller. Those are very important. First and foremost segment is the pin configurator segment, and next segment is the code generator segment, and the next segment is the file segment. So these three are the major segments that is generated for your microcontroller. So this pin configurator segment is useful for visualizing the configurations that has been done for your particular microcontroller. So when I double click on this device top view, you can clearly see this is the layout diagram of my microcontroller RL78 bar F14, that is R5F10PPJ. You can see each pin description has been provided right over here. Once the configurations is done, you can see the configurations that has been done as a whole in this layout. So for that purpose, this pin configurator has been provided. So using this code generator segment right over here, you will be able to generate your own base peripheral software that is required for your microcontroller as per your user application. So I will be showing you how to configure your microcontroller in a while as per your application needs. But before that, we just want to do some basic configurations that needs to be done for almost all the programs. Just double clicking on this clock generator tab inside the code generator and you can see these configurations, that is the default configurations that needs to be fixed in the microcontroller before moving on. So let's take an example. This particular PIOR00 is yet to be assigned to the function TI00 and the respective port pin for that function is P17 by default. So if you need any alternate port pin to be configured for this function, let's check it out. Just click on this drop down. You can see the alternate pin that can be assigned with the same function is P66. So if you want that particular pin to have this feature, you just want to select that. So most often we will not be changing anything right over here. We can use all these functions for all these pins as it is. So if in case anything is required, I will just intimate you in future lecture videos. But for now, we will be fixing these settings by default. Just click on fix settings for fixing these settings as default settings in this microcontroller. Once that is done, just click on chip debug settings tab right over here. And this is a tab which is useful for enabling the debug option in your microcontroller. So if this is disabled, you will not be able to program your microcontroller using debugger, or you will not be able to debug your microcontroller using debuggers like E1, E2, E2 Lite, etc. So for that, just click on used radio button right over here. In my case, I'm just going to select the E1 right over here. If you are using any other emulators like E2 or E2 Lite, you just want to select the respective radio buttons right over here. So in my case, I'm just leaving this to be E1 selected. That's all about the basic configurations that you want to do. In addition to that, just double click on this watchdog timer right over here in the project tree inside the code generator, and you can see by default this watchdog timer is enabled or it is used by the code generator. So you just want to disable it. So I will teach you what is this watchdog and how to configure this watchdog in this microcontroller in a separate video. And for now, for almost all the videos, I will be disabling this watchdog, and in a separate video we will learn how to enable the watchdog and how to utilize its features for safeguarding our microcontroller. That's it. These are all the required basic configurations that you want to do for almost all the programs. So now let's just move for configuring our microcontroller as per our application needs. Now that the basic configurations required to be done for the microcontroller is complete, let us do the configuration required for generating pulses of required frequency and duty cycle with the help of PWM module available in timers of this microcontroller. So before that, we are just going to utilize this particular LED2 which is mounted on the development board, which is connected to P67 port pin of the microcontroller for demonstrating the PWM generated from the output pin. So I will be configuring this particular P67 pin as output pin, and we will be demonstrating the PWM generated, that is the PWM wave generated from the timer module of the microcontroller with the help of this LED2 available or mounted on this development board. So go to the ports right over here and move to the port 6 tab and click on this out radio button in the P67 pin layout tab, so that this particular pin P67 will be configured as output pin in our configuration design tool. And for configuring the PWM module, just double click on this timer right over here, and you can see various timer array unit 0, array unit 1, TMR J0, TMR D0, TMR D1, and we are just going to utilize this TAU0, that is timer array unit 0. And in this channel 0, just click on the drop down box and select PWM output master. And as soon as you select the PWM output master in the channel 0, you can clearly see in channel 1 the PWM output slave will be selected automatically. So when you click on this channel 0, you can see as a subdivision we will be having channel 0 as master and channel 1 as slave. So this master will be setting the period of the pulse generated, and this particular channel 1 slave will be setting the duty cycle of the pulse generated. So you can clearly see the period of pulse generated will be 100 millisecond and the duty cycle of pulse generated will be 50%. So I am just going to leave it as it is. I am just going to generate pulses of period 100 millisecond with the duty cycle of 50%. That is, for 50% of 100 millisecond the pulse will be on, and for rest of the 50%, that is for 50 millisecond, the pulse will be off. So this is the type of pulse that we are going to generate now. So I'm just going to click on generate code for generating the base drivers required as per the configuration done. So this is the main function generated for writing our user program, and move to the timer user.c. You can clearly see there will be two interrupts generated. One is the channel 0 interrupt and another one is channel 1 interrupt. So this particular channel 0 interrupt is useful for setting the period as I mentioned, and this particular channel 1 interrupt is useful for setting the duty cycle of the pulse generated. So in these two channels I will just toggle the state of the P67 pin. So P6 is equal to P6 XOR of 1 left shifted by 7. So again I will do the same inside this channel 1 interrupt also, and in the main function I will start the timer. So this is the function required to start the timer, so I will call this function just before this while of 1 inside the main function of the program. So as soon as this particular function is called, the timer will start counting, and as soon as the timer starts counting, for every 100 millisecond this particular channel 0 interrupt will be called, and this particular P67 will be toggling its state. If it is low, it will become high. If it is high, it will become low, as per the program written right over here. That is the programming line written inside the channel 0 interrupt. And as soon as the timer starts from 0 or it reaches 100, this will happen, and in the mid of the timer, as per the configuration, for every 50% duty cycle of the pulse generated, this particular interrupt will be called. So again the same pin will be toggling its state. Hence we will get a pulse of 50% duty cycle generated from the output pin P67 of the microcontroller. So let me just compile this program first. I have already connected the E1 emulator and the development board to my PC through USB cable. I'm just dumping the program to the development board microcontroller by clicking on F6 in the keyboard or this particular icon right over here. And now let us visualize the output in the hardware. Now you can see this is the output which I got in the hardware for 50% duty cycle for the pulse generated for 100 millisecond. Pulse generated with period of 100 millisecond. So the LED2 which is connected to P67 of the microcontroller is blinking at a rate of 50 millisecond. And you can see the oscilloscope output 10 Hz pulse has been generated with 50% duty cycle for 100 millisecond pulse, period pulse. I am just running the program. So we successfully demonstrated a 50% duty cycle pulse generated from the P67 pin with the help of PWM in timer array unit 0. So now what I'm going to do is I'm just going to change the duty cycle. So let me just change this particular duty cycle to be 25%. So now what happens is the pulse generated will be turned on for 25 millisecond and it will be off for 75 millisecond. I'm just dumping this. Let me check this output in the hardware. I'm running the program. You can clearly see this is the hardware connections that I have made. The probe of the DSO from the oscilloscope, the probe is connected to CN1 connector pin number 31, which is nothing but the P67 of the microcontroller, and the ground of the probe is connected to ground of the development board, and the development board is connected to the emulator to which we will be debugging the code, and it is powered up. This development board is powered up with the help of this 5 volt 3 amps SMBS. and this oscilloscope is powered up, and also the development board is powered up with the help of this SMPS. So this is the setup we have. Let's demonstrate the output in the hardware. Now you can see on the development board, this is the output for 25% duty cycle pulse generated for 100 millisecond period pulse. And this is the oscilloscope output. Same 10 Hz frequency pulse has been generated, but this time the duty cycle is 25% and the period is same 100 millisecond. Now I'm just going to reduce the duty cycle further, that is I'm just going to reduce the duty cycle of pulse generator to be 10%. Now what happens is the pulse will be turned on for 10 millisecond and it will be turned on for 90 millisecond. I'm just downloading this particular program to the microcontroller in my development board. And I'm running this program. Let's check the output in the hardware. You can see this is the output which we got for 10% duty cycle pulse generated, and this one is the oscilloscope output. The frequency is 10 Hz, which is same, and duty is now 10%, and the period is same as 100 millisecond. And now when I try to increase the duty cycle, let's say to be 75%, and when it generate the code, now what happens is the pulse will be turned on for 75 millisecond and it will be turned off for 25 millisecond. Now I am dumping the flash. And I am running the program for visualizing the output in the hardware. You can see this is the output which we got for 75% duty cycle pulse generated. Since this LED will be turned on only when providing a low signal, on increasing the duty we will get the LED dimmed up, and on decreasing the duty we will get the LED lighted up properly. So that is why now we are getting a light blinky type LED on 75% duty cycle of pulse generated, and this is the oscilloscope output. You can clearly see the frequency is same 10 Hz, duty is 75% and period is same as 100 millisecond of pulse generated. So till now we generated pulses of required period, fixed period and duty cycle with the help of PWM generated interrupts, and now we are just going to write some program for changing the duty cycle in the runtime of the program. So what we will do is we will just try to change the duty cycle of the pulse generated from 0 to 100%, and as soon as it reaches 100%, we will try to change the duty cycle from 100% to 0%. So for that we just want to note down some of the registers in which we will load the timer load value for changing the duty cycle. So move to the timer.h and search for TDR0. You can clearly see this is the 16-bit timer data register for timer 0, and this is the 16-bit timer data register for timer 01. So this will set the period of pulse and this will set the duty cycle of the pulse generated. As we know, channel 0 of the TAU0 is meant for period and channel 1 is meant for duty cycle. As per the configuration, channel 0 we are setting the period of pulse generated, and in channel 1 we are setting the duty cycle. So as per the configuration, 75% duty cycle we are having the load value to be 927C. So 9 to 7C is nothing but 37500, and C34F, which is the period. Let me check what is the value. C34F. So this is the maximum value, right? So 49,999 is the maximum period value to which the timer will run from 0. So this is the maximum period value. So timer will run from load value 0 to 49999. So this is the maximum period value, and the 75% duty cycle is having the value 927C, which is nothing but 37,500. So as per the calculation, until the load value 37,500, we will be having high pulse, and for the rest of the pulse we will be having low pulse. So this is the expectation. So as per the value available in this TDR01 register, the pulse will be turned on. So when you have a value of particular, that is 50% of this particular value in this TDR0, we will have the duty cycle of the pulse to be 50%. When you have 25% of this particular value in this TDR01, we will have 25% duty cycle of pulse generated. So this is what the expectation is. So now we are having 75% of this particular value loaded in the TDR01. So that is why we are getting 75% duty cycle in our PWM pulse generated. So in run time, we will be changing this particular TDR01 register value. So let me just go to the timer.c and try to find out TDR01. You can clearly see this is a register to which we have loaded this particular value. So our motto is change the value of this particular TDR01 from 0 to the maximum value loaded in TDR00. The maximum value loaded in TDR00 is this particular macro. When I search for this particular macro in this timer.h, you can clearly see this is the value of this particular macro. So in TDR00 we have C34F, which is 49,999. It is almost 50,000. So here I will write down a loop I is equal to 0, I less than 49,999, and I will write the value of I to this TDR01, and as soon as I write down the value of I right over here, I will just call a delay function of that is a rough loop delay function of 10 lakh. Let's say it to be 10 lakh, and this is the loop which will change the value of the duty cycle from 0 to maximum. And as the next step, we are just going to change the value of the duty cycle from maximum to minimum. So what I will do is I will just start the count from 49,999, and I will run till I greater than 0, and I will decrement the I value, and I will do the same operation inside the for loop. So here I will just uint16 underscore t declare I, and I will write down the rough delay function while of t minus minus. So we have started the channel 0 right over here already, and this will change the duty cycle of the pulse generated from 0 to maximum, and this will change the duty cycle of pulse generator from maximum to minimum. So as per your requirement, just vary the delay value right over here. For me, it looks fine right over here. If you feel you are having a much delay or reduced delay, alter this loop value for better visualization in the fading of LED from minimum to maximum and maximum to minimum. So this looks a little weird, so let me just change the period right over here. So when I keep the 100 millisecond, the LED looks to be blinking. So I want the LED to be fading like that. So I'm just changing or reducing the period of the generator pulse to be 1 millisecond. Now when I dump this particular program, yeah, now it looks good. You can clearly see this is the output which I got in the hardware. The onboard LED is varying its brightness from maximum to minimum and minimum to maximum as per the duty cycle of the PWM wave generated. You can clearly see this is the output which I got in the hardware. The onboard LED 2 of the development board which I am using is dimming and brightening as per the logic that I have written. And parallelly you can see in the oscilloscope the pulse duty is also varying. So this is the output which I got in the hardware. The onboard LED is varying its brightness from minimum to maximum and then from maximum to minimum using by varying the duty cycle of the PWM pulse generated. So this is the output which I got in the hardware. You can clearly see the duty cycle of the PWM waves generated from the timer array unit is varying from minimum to maximum and then from maximum to minimum as per the logic written. So I hope you learned some basic techniques for generating PWM waves of required period, duty cycle and frequency in Renesas RL78 by F14 series microcontroller in this video. See you in the next video. Thanks for watching.